So my goal today is to get to the bottom of this list, the threshold state. At breakfast, we were debating, if you want to identify where there's a phase transition between activity persisting forever and activity dying out, is it better to approach the critical point from below or from above? So there's plausible arguments either way. I mean, from above you have dynamics that are happening forever, so you can try to use those dynamics. On the other hand, from below, you never have to worry about violating the Abelian property. So the advantage of not having to worry about dynamics because things die out is that you can work with just the final state and not worry about in what order you're performing your updates. So anyway, this talk, the threshold state will be approaching from below, and it's an interesting question how to get a corresponding state approaching from above. Okay, so that's the vague philosophy, but let me say what are the two Markov chains I'm going to work with. So the first one is, I call it the free chain. You might also call it the open chain because or the closed chain because it has closed boundary conditions. Or you often see it called the fixed energy sandpile. Those are other names for it. So both of these chains will take place on sandpiles on a finite connected graph. And the state space will be okay, I can make it bigger than necessary. So if you want, the state space can be just all sandpiles on this graph. And the dynamics are like this. So k will be my discrete time parameter. And if I want to advance time by one step, I add a chip at a random site, say I, k, and then I stabilize. So the ingredients of this equation are, so ik, this is, these are independent uniformly random vertices. So I drop a chip at a uniform random vertex. That's like sprinkling sand grain on my pile. And then I try to stabilize it. So that this curly S means stabilize by topplings, if possible. So we saw yesterday that some sandpiles stabilize infinitely many topplings, and other ones don't. So if your SK happens to be a sandpile, or SK plus delta IK happens to be a sandpile that doesn't stabilize, then this S is just do nothing. Okay? So once you reach a sandpile that topples forever, your Markov chain is no longer doing anything interesting. If you want, you can keep adding your chips at random vertices, but there are no more topplings in this the way I've written it. that's okay because we're going to be interested in only running our chain up to the first time when you fail to stabilize. So the main object or time of interest will be the threshold time. How, which is the smallest k, such that sk does not stabilize. Yeah. Okay, stabilize if possible means that you perform topplings. I didn't tell you in what order to perform them, because we will see it doesn't matter. But if you want to fix an order, then you can perform them, say, okay, so this is a good question. How do you know if you're looking at a sandpile, whether or not it's going to stabilize? This is a very good question. It turns out there's an efficient way to check this on, on any finite undirected graph. And one thing you could do is you could start performing some topplings, and if you at any time reach a state where every site has toppled at least once, then you will not stabilize. So, one of two things will happen. Either you stabilize, or you can detect that you're never going to stabilize by this criterion. Okay, I think let's separate two issues here. One is we're going to define this mathematically, and it's well defined mathematically. Another issue is, how would you implement this Markov chain on a computer, right? And I think that's what your question is getting to. And in fact, one could show that as long as your graph is undirected, which is our setting, then in polynomial time, you will reach one of these two situations. Either you have stabilized, or every site has toppled at least once. And so this gives you an efficient way to implement it. But you're right that it's non-trivial to prove that, and well, we'll see some ingredients of the proof. And you might complain polynomial time is not efficient enough for you. You want linear time. Okay, that's okay. But just as a mathematical object, this thing is well defined, as long as you believe the Abelian property. So I keep putting off the proof of Abelian property, but I'll get to it later today. So Abelian property is what ensures that when you do this stabilizing, that the final state that comes out doesn't depend on your choices of what to topple in what order. Okay. Now, maybe as a check that everyone's following, how do we know the threshold time is finite? Right. So there's no way for sand to exit the system in this setup. So if you measure the total amount of sand, so I'll use absolute value for that. So absolute value of a sand pile just means total number of chips. Well, we're adding one chip at each time step, and topplings conserve chips. So, after k time steps, you have k chips more than you started with. Okay, and just by pigeonhole principle, if you have too many chips, you will have to explode, right? So note pigeonhole. If S is any sandpile with strictly more chips than, let's call it S max. So S max is the sandpile with degree -1 chips at every vertex. So this thing is the sum degree of x -1. If you have strictly more chips than this, then, well, some site is going to be unstable. So some x in V has at least degree of x chips. And that will be true no matter how many topplings you do, because topplings conserve chips. So a sandpile with more chips than this has to explode. Okay. So that ensures that, we have this upper bound. Once you get as many chips as S max, one more chip will make you explode. Of course, you may explode far before that point. So, and what we are interested in is, what can we say about the distribution of S tau, the sandpile at this threshold time. And another thing we can ask about is the distribution of I tau, which is the last vertex where we add that final chip that makes it explode. So this S tau is what I call the threshold state. And this I tau I call the epicenter. So, this infinite avalanche that you get at the end when you're exploding, think of it, it's like some big earthquake, okay? It's a giant disaster event, right? So, where did that disaster start? Well, it started by adding this chip at the last vertex, I tau. So, it's like the epicenter of the earthquake. So you could think of, the threshold state is some model of like, what does a system look like right at the moment when a large disaster is triggered? That's what it's modeling. Okay, so that's what we're aiming for, is some description of the distribution of these two random things, a random sandpile S tau and a random vertex I tau. Yeah.
What is large?
What is large? Well, I mean, it's a finite graph, so you can't be bigger than the whole graph. And, when you drop that final grain of sand at I tau, you cause topplings that persist forever. So you get an avalanche that spans your whole system, right? So it's as large as it can be, given that we live in this finite universe. Okay, so what's next on my list? Okay, the other Markov chain, right? So, these questions of this sort could be difficult because, well, on the one hand, abstractly the picture is, you have this state space. This state space is infinite, but you could reduce it to a finite state space pretty easily by, not allowing negative chip counts and not allowing very large chip counts. And so you have the state space, and then some of your sandpiles stabilize and other ones don't. You kind of have it partitioned. So here are the ones that stabilize. And here are the ones that explode. And you start, you start up here in the stabilizing part of the space, and you're doing some kind of random walk, right? So, you move around in this big space, and eventually, you hit the exploding part, and that's at time tau. Well, so this path has a length tau, and this point is S tau. This point here was S0. And, we just want to know how long does it take to hit this set, where do you hit it, and, things like that. So if sigma were a small size space, this would just be a linear algebra problem, right? So you can write down a system of linear equations that will tell you, exactly the probability of hitting this set in any particular point. So the difficulty of this problem is from the largeness of the state space. So their number of equations in your system is like the size of your state space, which is exponentially large in the size of the graph. So, so in general, like a problem like this could be intractable just because it's such a large system. What makes it tractable in this case is that we can compare the free chain to something we understand much better, the wired chain. So you could also call this the open chain, or in contrast to fixed energy sandpile, you might call it like driven dissipative sandpile. And this one allows sand to leave the system. So you pick a sink vertex, we call it Z, and you update by the same rule, except that your stabilization rule doesn't allow the sink to topple. So this curly S sub Z means stabilize without allowing Z to topple. Right. So this is a very natural question. I mean, how do we know that exploding is not possible in the wired chain? So we know in the free chain you can have a sandpile that just topples forever without ever stabilizing. And we hope that by allowing this sink, we've ruled out that possibility. Indeed, we have, because we assume our graph is connected. And so here's the sink. So we have this finite connected graph. And, well, suppose you were exploding. So suppose toppling persists forever. There are only finitely many vertices, okay? So in that case, some vertex would have to topple infinitely often. Okay? Maybe it's this one. But if X topples infinitely often, every time it topples, it gives a chip to each of its neighbors, okay? So then each of its neighbors will receive infinitely many chips, okay? So they will each have to topple infinitely often. So the property of toppling infinitely often is infective. It infects all your neighbors. Okay? And so eventually, by connectivity of the graph, you get to the sink. And the sink, not only does it not topple infinitely often, it's not allowed to topple at all. Okay? So hence, there was no such X that topples infinitely often. So the advantage of this chain is that you can run it forever. Okay? You don't have to stop when things explode because they never explode. And so, we like that because, well, a Markov chain you can run forever. It has a stationary distribution, right? So this guy has a stationary distribution. Call it pi z. And, well, it turns out we know a lot about this stationary distribution. So these are, well, so this is one of Dar's theorems that's on that list. So I'll state the theorem now, and hopefully we'll get to the proof. So of course, Markov chains have recurrent states, and they can also have transient states, and this one does have some transient states. So those have probability 0 in the stationary distribution. And all the recurrent states, so these are the recurrent states, all the recurrent states occur with the same probability, 1 over kappa, where, so kappa, if you like, is the number of recurrent states, but it also happens to be another interesting number. So kappa turns out to be the number of spanning trees of your graph. Okay, so I hope to get to the proof of these facts. They were discovered by Dar in 1990, and but for now, let's take this as take it as a black box. Basically, it's saying we have a good handle on pi z, and so what we would like to do is find a way to transfer as much information as possible from our understanding of this wired situation back to the free situation where things can explode. Okay? The sink, yeah, so sand will kind of pile up at the sink, right? And we're not allowing it to topple, but you know, it could have a huge pile of sand on it. So, you know, if you want to draw a picture of the wired chain, you know, think of you've got a table, and your sandpile is resting on this table. So you're dropping sand on the top, and then it causes some avalanches, and maybe some sand kind of trickles off the edge of the table, and your sink is like the floor. So you could have a big pile of sand on the floor, and you're for now, you're ignoring that pile, but when we compare the two chains, we're going to have to look at the floor eventually and see what happened there. Questions? There's various statistics you could compare for these two chains, but let me just perhaps unfairly focus on one particular statistic, the density. So, so each chain has a density. So there's a, you know, there's a threshold density, which is basically how much sand is there in the threshold state. And let's divide it by the number of vertices. So that way it's, you know, number of chips in the threshold state divided by number of vertices. And there's also, so that's for the free chain, and there's also a stationary density. Which is, you know, how many chips are there on average in this stationary recurrent state? Let's just look at expectation for now. So, question over here? Deepak? Question? Good? Okay, so because we know this stationary distribution is uniform, so this density is just, you know, it's a sum over all of these recurrent states, R and RZ. And I guess I also want to divide by the vertices.
And a large element is the one which is the first time near the boundary side. But that might depend on what is the, if the intermediate is well embedded and as said, could be stochastic variable, which is a distribution.
Okay, so by large avalanche, we mean really large. So, if one sand grain falls on the floor, I don't consider that large necessarily. To be large, you have to have a system-spanning avalanche. So, yeah, I agree. Yeah. Okay, so tau is a random time, right? Yeah. So that's exactly what makes this comparison potentially problematic. That the threshold time is random, and so the distribution, even if you couple the two chains, which we're going to do, the distribution at a random time could be different from the stationary distribution. And we'll find it is different, but in a predictable way. So you can express one as a size biasing of the other. In some sense, you're seeing the future difficulty that I didn't address yet. It's an expectation. So tau is a random time. Right? So as tau is a random sandpile, I take its expected number of chips. Okay, so these two things, I fix a graph and then I get two numbers. Okay? And, well, I don't know what you would expect. Maybe, if you're very optimistic, you might just expect them to be equal. That's not right. But maybe you'd expect in some limit of large system sizes that they would have the same limit. More surprisingly, that's not right either. So let me tell you the situation on Z2. So example, let's take our graph to be a box in a square grid. You've seen this square grid picture in possibly every talk so far. So in that situation, here's what we know. So maybe I'll give these names. Okay, so the threshold density I'll call zeta tau, and the stationary density I'll call zeta s. So I'll do zeta s first. So as n goes to infinity, zeta s converges to kind of mysterious rational number 17 over 8, so 2.125. So on average, in the stationary state, on a really large square grid, you have 2.125 chips per site. And this was conjectured by Grasberger in the 90s. And it was proved a few years ago by several independent groups. Kenyon Wilson, Bogosian, Prijev, and Ruel. And I think there was even one more group. I'm blanking on it at the moment. Okay, so that's the situation for the stationary density. Now, you can measure the threshold density in experiments on large grids. And if you do that, you find it agrees quite well with this value. But if you take your grids really, really large, you start to see a difference. So, they start to be different here in the fourth decimal place. This is kind of puzzling. Like, why are these values close if they're not actually equal. So in the next, for the rest of this talk, and maybe it will spill over a bit to my next talk, I want to, I want to state a theorem that says that, first of all, it will say, although they're not equal in this particular experiment, if you change the experiment a little bit, you can make them equal, provably equal. So that's going to be the first message. And the second message will be, in the cases when they're not equal, what accounts for this difference? Okay? So, so first, how can we make them equal? Well, you might suspect that the reason for the discrepancy has to do with slow mixing. Okay? So here's a story which is basically accurate. Okay? You can couple the two Markov chains, then you can run them coupled, and at the threshold time, well, you're stuck. You have to stop the free chain and take your measurement. And what may have happened is that your other chain, it got pretty close to the stationary distribution, but it didn't get all the way there. Okay, it's not quite mixed, and so instead of seeing the true stationary value, you see something close but not equal. So let's try to take that heuristic story and turn it into a precise statement. So how could you give it more time to mix? Well, you have to realize that theta tau depends on where you started. Okay, so initial state is potentially going to make a difference. So it's natural in experiments to start with the empty initial state, just 0 chips. Okay, but 0 chips, might not give you enough time to mix, right? And so if you want to give yourself more time to mix, then you could take the chip counts negative for the initial state. And then it will take long to reach the threshold, and then you might expect this discrepancy to go down. So this is exactly the experiment that was done by Pogosian, Priege, around 2010 or so, maybe 2011. So what they did is they measured zeta tau of a constant chip configuration H, and they found, like if you take H large and positive, then you get a very bigger discrepancy, and if you take it to 0, you get this small discrepancy, and if you take it negative, it becomes even smaller. And so they conjectured that this thing in the limit as h goes to minus infinity, you recover this stationary value, zeta f. Yes? What's the boundary here? Thanks. Yeah, so the boundary is everything on the outside. So really, to honestly draw this graph, I would have to add a bunch of edges like this. So from each corner, there are 2 edges to the sink, and from each side vertex, there's 1 edge to the sink. So that's why I call this the wired chain. You're taking the boundary and you're wiring it. The terms free and wired are borrowed from the literature on uniform spanning trees. Okay, so what? Oh, no. Thank you. Wow, good eyes, Leo. Okay, so this is what they conjectured, and I liked this conjecture, and I found, I liked it because, in a way, it was disappointing to see this, to discover this difference. Like, this difference, to connect it to my personal story that I started with yesterday, after PhD, this was kind of like one of my first goals, was to prove, that these things are actually equal. Because, at that time, 2008, 2009, we didn't have experiments, okay? So we didn't see this difference in the fourth decimal place. And it looked like they're equal, and that was really intriguing to me. But, after thinking about it, I couldn't even come up with a plausible route to proving it. And then with Anna Fey and David Wilson, we found some kind of toy graphs that are much simpler than the square grid, where they're not equal, and you can even prove that they're not equal. So then we got just suspicious that, why should they be equal? And David at that time was at Microsoft Research. He had a lot of computing power at his fingertips, and so he designed some very large experiments to find this difference. So in a way, that was disappointing for me that, well, this thing I wanted to prove was actually wrong. So then when these guys came along and kind of salvaged the conjecture, I was excited again and decided to try to prove it. So, yeah. Oh, good question. Yeah. So is it always the case that zeta tau is bigger than zeta s? No. So you can cook up graphs where zeta tau is smaller than zeta s. So I don't know if it's significant that it's bigger. Yeah, so you could, So it may be the case on the square grid, for example, that zeta tau of h is monotone in h. I don't know if that's true, but I think you can cook up graphs where the inequality goes either way, and actually where this function is not monotone. So I don't see any reason for it to be monotone. Other question? Okay, so I'm going to tell you. Okay, so the first message is this is true, and I'll state a theorem that implies it, and I'll try to show you the main ideas that go into the proof. So. So to prove this, let's try to be more ambitious. Instead of just looking at this one statistic, the density, let's try to look at the whole distribution of these things, S tau and I tau. Okay, so I'll call this the coupling lemma, which relates the two chains. So in some sense, this is the basic engine that makes everything work, and it would be really interesting to adapt it to other sandpile models. So this is the portion of the proof that is specific to the deterministic Lochtang-Wiesenfeld model, this lemma. Okay, and it says the following: for any sandpile, you can decompose it into three pieces. So there's a unique triple R, M, and V. So R is can you see at the very top here? Okay. R is so you say, fix a sinc vertex and a sandpile S. So R is going to be a recurrent sandpile with respect to that sinc. M is going to be an integer, and V, this is a lowercase v, is going to be a function, going to be in VV, a function on vertices with, all right, this way, which takes value 0 at the sink. Okay? And okay, so there's a unique triple such that you can write S as a sum R plus M chips at the sink plus the Laplacian of V. Okay, so let's make that part 1 of the lemma. So what is this saying somehow? It's saying for any sandpile, it has a recurrent version, R, and if I want to go from the recurrent version to the sandpile S I started with, then I need to make 2 modifications to the recurrent version. First, I need to add or subtract some chips at the sink, and then I need to add the Laplacian of an integer-valued function. So this part is where you should think of this part as performing topplings, okay? So you start with R, the recurrent thing, you add some chips at the sink, then you perform some topplings, and you arrive at your sandpile F. So let's call this recurrent version. So this is, well, so it depends on the sink. So it's let's say the Z recurrent representative of S. So let's call it R. RZ of S. Script RZ of S. Okay. Okay, second part of the lemma is you can detect stabilization from this decomposition in a very simple way. S stabilizes if and only if. Okay, so before I write this condition, I need to fix the convention. So the recurrent sandpiles, they don't pay attention to the sink because they live on the wired chain, and the sink is the floor, and they don't see the chips on the floor. But if I want to make sense of this equality, I mean, this is, S is defined everywhere, including at the sink. So I need to make this part defined at the sink. So my convention is going to be that a recurrent sandpile always has exactly degree Z chips at the sink. Okay, and now once I've fixed that convention, then I can detect whether S stabilizes just by looking at the M part of the decomposition. So S stabilizes if and only if M is non-negative. And the third piece is the coupling itself. So I can consider 2 operations. One operation is adding a chip at some vertex I and stabilizing. That's the operation that drives the chains. So let's call this AI. So let AIS be stabilization of S plus delta I, and AIZS be the same thing, but stabilizing without the sink topple. So then something very fortunate happens, which is this RZ function takes AI to AIZ. So let's see. So how do I write that? RZ of AIS equals AIZ of RZ of S. So it's a kind of commutative diagram. If you add a chip at I and stabilize in the free chain, and then you look at the recurrent representative of whatever you get, that's the same as first taking the recurrent representative and then adding a chip and stabilizing in the wired chain. So whenever you have something like this, it gives you coupling of your Markov chains, right? So in particular, so hence, if SK is running the free chain, then RZ of SK, it's a function of a Markov chain. So in general, it need not be a Markov chain, but because of this identity, it is a Markov chain. And not only that, it is the wired chain. Okay. So this lemma kind of packages everything model specific that the proof needs. And let me tell you, well, okay, good. So I didn't state the more general theorem that implies this conjecture, but now we can state it. So here's the theorem. It's going to give okay, so start the free chain at some S0, and eventually we're going to be taking a limit as S0 becomes very negative. Right? So S0 is like the H here. And we're going to look at, well, we're going to keep track of this decomposition as we run the free chain. So we know the first part of the decomposition is the wired chain. And we need to know something about the second part. Because the second part is what governs the stabilizability, right? So indeed, the threshold time is nothing but the minimum, the first time that this MK becomes non-negative. Okay, so let's look at the following event. So we'll say we want to know what's the chance that the epicenter was a particular vertex I, and also the chance that the Z recurrent representative of the threshold state was a particular recurrent state R. And just because we can, let's throw in a little bit of information about the M. So we'll say, let's say we also want to know what's the value of M at the threshold. Now we know it's non-negative, but it could be bigger than 0. So what's the chance that m tau is some particular integer n? Okay, so that's the event we're interested in. And here's what it's going to equal in the limit. So first, we're going to take a uniform distribution over the i's. So, okay. So what are the quantifiers here? For all z, I, r, then we will take once we've chosen our I, we will take uniform distribution over the r's, except with a certain size biasing. So we're going to take okay, so the uniform will be this 1 over kappa, the number of recurrent states. And then the size biasing looks like this. So it's going to be the indicator of, we know this n has to be non-negative. And I'm going to upper bound it by something I call the burst size. So the burst size is the following thing. Okay. Let's just give it a name, B of IR. And I need a, let's see, do I need a constant? I guess the constant turned out to be 1. Okay, so this is the full statement. To tell you what B is. So, okay, so this is the burst size, which is the number of chips that fall into the sink when you add a chip at I to some recurrent state and stabilize it to get R. So let me write that down. So it's the number of chips falling into the sink when stabilizing A I inverse R plus delta I. So, okay, so when you stabilize this guy, so remember AI is, or it's AIZ actually. AIZ is the operation of adding a chip at I and stabilizing. On recurrent states, this operator is invertible. Okay? That's kind of the secret behind the uniform distribution that Deepak discovered. So there is a unique recurrent state. For any recurrent state R, there's a unique recurrent state for which, when I add a chip at I and stabilize, I will obtain R. So that's what this AI inverse of R is. Okay? And then I could count, you know, when I actually do that stabilization, some sand will fall off the table into the sink. Okay? That's the burst size. And why would you expect burst size to appear in this limit? Well, let's consider some extreme cases, right? So one case is that burst size is often 0, right? So sometimes I drop a grain of sand on my pile, and maybe it falls right onto a site that's less than degree minus 1. So dropping sand there doesn't even cause any topplings. It's clear that you cannot trigger any avalanche, much less the threshold avalanche, by such a move, right? So if you're going to trigger a big system-spanning avalanche, at a minimum, you need some sand to reach the sink. And this is saying, which maybe should be plausible, maybe not, I don't know. But it's saying that actually the chance that you trigger the system spanning avalanche at any particular pair IR is just proportional to the number of chips that fell into the sink in that last move. Okay. Okay, so now I can go in one of two directions. I can either sorry, this is my theorem from 2014. Part of my reason for highlighting it here is, like, it's the one thing I wrote which I wish people would read that they haven't. So, let's see. Okay, so there's a couple of things I could say from here. So one is, how does this, general thing imply this particular conjecture? That's pretty short, so maybe I'll do that. Yeah, so, right, so you might think that, why don't you have a 1 over z here, right? Like, it's not a product form because this, right? So this Bz depends on the I and the R. So, right, it's saying that certain pairs IR are more likely than others, right? Because, right, if Bz, I need a 1 here. So I want to say if BZIR is 0, then I want this indicator to not be satisfiable at all. So I guess I need a -1 there. Yeah, so you might want me to divide by something, but it turns out the correct normalizing constant is 1. So okay, so to make sense of this a little more, imagine, let's take a special case which will get us this conjecture. So, and that's the case where z equals I, right? So it's kind of like if you had a lot of foresight and could predict in advance which vertex was going to be the epicenter, then you might decide, well, okay, if the epicenter is going to be over here, let me take that vertex to be my sink vertex in the coupling. And then you get something much simpler where the size biasing disappears. Because when z equals I, well, how many chips fall into the sink when I drop 1 chip into the sink? 1, right? Nothing happens when you drop 1 chip into the sink. There's no topplings and just 1 chip falls into the sink. So, so then there's no size biasing, and you get uniformity, right? So a particular, so the corollary where I equals z is just saying, the chance that the threshold state is I, and now you have to take the I recurrence representative. Then you just get uniform in the limit. This is kind of, in our naive first guess at how the two distributions might be related, this is kind of what we were aiming for, right? I mean, the stationary distribution of the wired chain is uniform. And, indeed, you do get this relationship in the limit, but you have to take z equals I, otherwise you don't see it. And a kind of interesting aside is I don't know how to prove, I mean, this corollary is much simpler than this weird burst size statement, but I don't know how to prove this special case without proving the whole thing. So. Okay, and now if you integrate out the I variable, then, well, what you see is that not only is the density converging, but the whole distribution of the chip counts is converging. So, but actually that's secretly using an interesting fact, which is Marinos theorem. So, well. Okay. So Marinos theorem says that certain statistics don't depend on the choice of sink. Namely, if you take a sum over all recurrent configurations of some, so take a generating function like some variable t to the power of the number of chips in the recurrent configuration, then what you'll get is, well, you'll get some polynomial in this variable t. Actually, let me call it y, because it's the y variable of the polynomial that comes out. And this, in particular, the right side doesn't depend on the choice of sink. So if you combine this with Marinos theorem, what you'll get is that, if you take the number of chips in the threshold state, that will converge in distribution to the number of chips in the uniform recurrent state. Again, as S0 goes to minus infinity. So this guy here is the uniform recurrent state. And, you need Marinos theorem precisely because, so the point is this distribution of the number of chips in uniform recurrent state by Marinos theorem doesn't depend on the choice of sink. Okay, maybe a couple other comments. So, one of the themes of the workshop is universality, and universality in general is like, something that different fields mean different things by. So, the abelian sandpile is something that seems to not have very much universality. In a couple different senses. But here's a kind of weak universality that you can pull out of this statement. And that is, the nature of this limit. So the only thing that needs to go to minus infinity in this limit is the number of chips in the initial configuration. So you don't have to take your initial configuration to be this constant h. You could take any initial configuration you want, even with some very positive heights. As long as the number of chips is tending to minus infinity, you'll get the same limit. And so, since I said the abelian sandpile doesn't seem to have a lot of universality, what do I mean by that? Well, one symptom of that is lattice dependence in the scaling limit. So if you compare the divisible sandpile, which Violetta talked about yesterday, with the abelian sandpile, they have different limit shapes. So you can consider the following experiment in ZD. You start n chips at the origin and stabilize by topplings. If you do that with the abelian sandpile, you will get a beautiful fractal-looking picture with all these different patterns in different places that I alluded to yesterday. And we know that by work of Pegden and Smart, we know that picture has a scaling limit. So if you take n, the number of chips, to infinity, and you rescale space by factor of, to make the total volume n down to 1, then that picture has a weak star limit. But, we strongly believe the limit is not spherically symmetric. It obviously isn't from the pictures, and we know it's lattice dependent, so it would be a miracle if it happened to be a perfect circle. Nevertheless, some mathematicians still nag us because they say, you understand so much about the sandpile, so prove it is not a perfect circle. And my response to, or I guess my co-author Wes Pegden's response to that is, no, since we showed it's lattice dependent, now the onus is on anyone who claims it is a circle to prove that it is. Okay. In any case, the divisible sandpile, which is the same model, but you now allow your chips to be divided as finely as you want. If you do the same experiment, you will get very nearly a perfect circle. So not only is the scaling limit a disk, but the error is only constant in the radius. So that was an aside about universality. But here's a kind of foreshadow of it, that you get some universality in that dependence on the initial condition washes out of this limit. Okay, so there are two things I want to do, but I have time for like half of a thing. So the two things are, one, tell you how to prove the coupling lemma. So that's the model-dependent stuff, which, none of it is very hard once you read Deepak's 1990 paper. It's all there. But it's a lot of, it's many simple steps that fit beautifully together. So that's one thing. And then another thing I would like to do, which maybe is more feasible in the few minutes remaining, is tell you the general tool, the not model-dependent tool that goes into proving limits like this. So that tool is the Markov renewal theorem. So, okay, good. So time for discussion. So one possible thing to discuss is I can state for you the Markov renewal theorem and explain how this limit is just a special, it's just a straightforward application of it. Are there other things people want to discuss or questions? Oh, good. So I have another hour. Thank you. Okay. Okay. All right. So pause for questions before I say a few words about Markov renewal. Yes.
Will you speak for another hour and let me skip my talk?
That would be that I want to see your talk. That's the problem. So Chris is talking about frogs on trees, and we don't want to miss this because we don't want to miss it. Other questions? Okay, so Okay, so here's a very general situation that, well, it comes up a lot. It just happens to come up in this sandpile question. But the general situation is you have a Markov chain on, say, some state space sigma, and you have some additional data of a length function on edges of sigma. So length function, let's say L. So for each pair of states of your Markov chain, it gives you a non-negative integer. Maybe it's not even defined on, like, it only needs to be defined on transitions of the chain. So it's defined when, so L of xy is defined whenever your chain has a chance of transitioning from x to y. Okay, and then you can track how much length your chain has accumulated. So, so let's say your Markov chain is xn, and you can track this random quantity, lambda k, is the total length traveled in the first k steps. L of xk minus 1, k. Okay, and then you can imagine, you have a finish line. So, instead of stopping your Markov chain at some deterministic time, like after 1,000 steps, you're going to say, no, I'm going to stop it at a random time, namely, the first time I traveled total length 1,000. So let's call that, so I don't know, pick some big integer, capital L, and let, I don't know, tau L be the first time that my total length traveled is bigger than or equal to L. Okay, and then I can ask, well, where am I likely to be at this particular time, tau L? So that's what the Markov renewal theorem addresses. Markov theorem. So it says, if your target length was really long, so you're taking L to infinity, and you're interested in the distribution starting from some x0 of, well, what could you ask for? So you could ask for which edge was the one that pushed you over the threshold. So let's say x tau minus 1 equals say x, and x tau equals y. And then you could also ask, well, by how much did you exceed your target of L? So you could ask for lambda tau, or lambda tau L. So you know lambda tau, well, it has to be at least L, but it might be bigger. So let's ask for that to equal some number n. All right, and then, this is one of these situations when you can guess the answer and then prove it's right. So how would you guess the answer? Well, you say, I'm running this long marathon of length. The total length has to be at least L. So I started somewhere, But if the marathon is long, I'm going to forget where I started. I'm going to be in the stationary distribution of this Markov chain. And then here's the finish line of my marathon, where this total random path has length L. And x tau is the first site I reach after the finish line. And x tau minus 1 is the last site I reach, before the finish line. And this length is what pushed me over the edge, right? So if you think about it, you should expect a size biasing, right? Like some edges might have length 0, and you cannot finish on those, because if you weren't over L and you travel a length 0 edge, you still won't be over L. On the other extreme, if an edge is really long, then it's more likely that your finish line will happen to fall on a long edge. So what you should expect to see is the stationary distribution, pi x pxy, but size biased by the length of the edge. So you should put an indicator here of n. The excess length should be, well, it could be as low as 0 and potentially as big as the length of the edge minus 1. Okay, so what hypotheses do you need for this guess to be correct? Basically, the minimum obvious things to require. So, first of all, you want your Markov chain to have a stationary distribution, or a unique one. So let's make the chain irreducible. Secondly, you might be worried about periodicity. So you don't want the following situation to happen, that no matter how so I consider all cycles that start at x0 and go and return to x0 and look at the total length of all the cycles. You need the GCD of those lengths to be 1. So that's kind of the aperiodicity condition. So let me write that down. So so here's the main assumption you need on L, GCD of lengths of all cycles equals 1. And yeah, I guess that's it. So so that's what the theorem says. And I think, hopefully the way I explained it, it seems almost self-evident why it would have to be true. And indeed, you can prove it just using the standard things you learn in the undergraduate Markov chain course. Like, you could prove it just using the ergodic theorem and the convergence theorem for Markov chains. You just apply those theorems to the right auxiliary chain. So, okay, so that's the theorem, and this thing is a direct application of it, where you choose. So in our sandpile situation, you choose L of. So the states are sandpiles now, right? So the edges are like, there's an edge from, say, a sandpile R to a sandpile AIZ of R, right? And the length function you use is the burst size, what did I call it? BIR. Okay, and why is that the right length function? Well, it's because of this way of realizing the threshold time, right? So, you know, your initial m value, m0, will be something very negative because S0 was a negative initial condition. You need a lot of chips at the sink to make it recurrent. And so you start from this very negative condition, and every step, some chips might fall into the sink. And every time that happens, mk is increasing. And your threshold time is the first time you cross 0. So the L, you know, capital L just plays the role of minus S0. One interesting oh yeah, do you need to normalize this? Yes, thank you, you do, right. So yeah, so there's no reason these should sum to 1 because I didn't make any assumption on L that would make them sum to 1. So indeed, I should divide this whole thing by z, and the normalizing constant is, you know, the sum over all edges of the x, p, x, y, l, x, y. So, yeah, so a fun exercise is, for this particular burst size choice of L, it ends up happening that z equals 1. And, well, it's not really very mysterious. The reason z equals 1 is that, on average, the burst size is exactly 1. Right? You're in stationarity, so when you drop a chip, then on average, you have to lose exactly 1 chip to the sink. So you average over the whole ensemble of i's and r's, then you'll get average burst size 1. Okay. Yeah, anything else people want to discuss?
Will be taken offline.